Hello everyone, my name is Taha Tekdogan. I am here to present our paper benchmarking Apache Spark and Hadoop MapReduce on big data classification. The organization of the presentation is much like the paper's organization. I'm going to introduce some concepts, discuss prior works relating to our study, methods we use for our experiment, evaluation techniques to identify the performance of frameworks, and conclusion with possible future directions. Nowadays, wide ranges of applications produce enormous amount of data that carry valuable information. We call it big data. There have been some data analytics tools to extract these helpful information from big data, such as Apache Spark and Apache Hadoop. These tools are evolving to adapt their functionality so that they become able to use data mining techniques for information extraction. We also have to consider a lot of parameters that affect the performance of the underlying framework. So we want to bring all these together and provide a comprehensive and task-specific benchmark study. But before that, let's briefly discuss some cornerstones. Big data is a field of analyzing and extracting information from large amounts of data that are too large or too complex to be dealt by traditional data processing software. There are huge amounts of data being generated every day. And since we're not strictly establishing standards for data being generated, they may be in any size, in arbitrary structure, and available for only a restricted time to process, like let's say milliseconds as in the search engine example. These features of big data bring some challenges with it. These challenges are defined as 5 V's, consists of volume to present the size of data, variety to present data being whether structured or unstructured, velocity to present the available time to process data, value is related with what an organization can do with that collected data, and finally veracity is the quality of data in this case. On the other hand, there are plenty of data mining algorithms to extract helpful information from data, such as classification, clustering, association, regression, prediction, and so on. We will be focusing on classification examples specifically in our study, and when we bring all these together, a definition for big data mining emerges as extracting useful information from large datasets, which was not possible before due to its volume, variety, and velocity. In 2015, Shi et al. Provided a benchmark to evaluate major architectural components in Spark and MapReduce frameworks, such as shuffle, execution model, and caching. They also provide two profiling tools. The first one is execution plan visualization to correlate task execution plan with resource utilization for both frameworks. And the latter one is fine-grained time breakdown to visually present this correlation. They show that Spark is about 2.5 times, 5 times, and again 5 times faster than MapReduce for workloads, word count, k-means, and PageRank, respectively. In 2016, Samadi et al. Employed HighBench to compare Hadoop and Spark in terms of performance based on criteria including execution time, speedup, and throughput. Their results show that Spark outperforms Hadoop, but with the trade-off of higher memory consumption. Liu's research investigates the differences between Spark and MapReduce along with ideal parameters to improve the efficiency. Common applications such as aggregation, shuffle sort, and iterative jobs are represented by workloads of word count, terasort, and k-means, respectively. Experiments show that Spark performs better than Hadoop for iterative and aggregation jobs, while Hadoop is a better choice for shuffle-sort kinds of jobs. In 2020, Ahmed et al. Provided a benchmark study using HighBench that aims to identify the parameters with the highest impact on the performance of Hadoop and Spark by using trial-and-error approach to tune them under a variety of experimental settings. Their evaluation metrics to measure benchmark frameworks' performance are execution time, throughput, and speedup. Their experimental results show that performance of the frameworks heavily depends on the workload size and the correct parameter selection. They show that Spark has better performance when the input size is small, and it can even get 14 times faster than Hadoop under certain parameters. Previous studies use benchmarks like HighBench so that their parameters are restricted to be very generic, like the execution time of the whole program, speedup, and throughput. This avoids them from studying the predominant components of the studied algorithm. Moreover, they don't examine the effect of scalability, which is vital for big data management systems. And they also use same dataset with varying sizes, like using Teragen to generate datasets of, let's say, 1 gigabyte, 5 gigabytes, 10 gigabytes, and so on. We define evaluation metrics by taking classification tasks into consideration, such as defining execution time, referring to the duration of the training phase, and measuring the accuracy score of the trained model. We also show that in a clustered environment, the number of clusters may have a significant improvement in performance. Datasets we used during our experiment are different real-world datasets to represent varying workloads. Let's dive into methods section. We compare the performance of Apache Spark and Hadoop MapReduce. So we use their respective software on our working environment. Their machine learning utilities are used to implement the machine learning models. We use MLlib for Spark and Mahout for Hadoop, respectively. We employ Naïve-Bayes Classifier as a machine learning model for both frameworks. That is a set of supervised learning algorithms based on applying Bayes' theorem with the naive assumption. 4 different datasets are used during the experiment. Heartbeat dataset from Statlog is a small-sized dataset with 75 kilobytes. We use it to identify overheads of frameworks designed for handling big data. URL reputation dataset is an anonymized 120-day subset of the ICML 2009 URL data with size of 400 megabytes. Web spam dataset contains web pages that are created to deceive web users and manipulate search engines, which has the size of 2 gigabytes. And finally, we use KDD12 dataset. That is a binary classification dataset to predict whether a user is going to follow an item in Tencent Weibo, which was a microblog website popular in China. It was originally used in KDD Cup 2012, named as Click-Through Prediction Competition with size of 2 and 1 gigabytes. We define 3 evaluation metrics to measure the performance of underlying frameworks and compare them. The first one is execution time, which refers to the time it takes to train the model, which is Naïve-Bayes Classifier in our case. The second one is accuracy. It is the success of the trained model on test dataset. In other words, how well we can predict with our trained model. We split our datasets by 80/20, 80% of data used for training and 20% of data for testing. The third metric is scalability, where we investigate the change in performance by adjusting the number of clusters in the system. We employed 1 master and n slave clusters, where n is a number from the set 2, 4, 8, and 16. Experiments are conducted on Amazon Web Services Elastic MapReduce clusters, and Amazon's S3 is used for storage. We repeated the experiment 3 times for each configuration and reported results by taking the mean value of them. Here you can see the ecosystem of our experiment and the environment setup of the experiments on AWS. Experiments show that Spark is much faster than Hadoop during the training phase. As the workload size gets larger, execution time grows linearly for Spark. A similar execution time growth pattern is observed for Hadoop MapReduce, but with much longer time durations. However, Spark's performance degrades when the input size gets larger. This is because the way Spark reads the input files and distributes over RDDs, which creates features that reside over distributed clusters memories and depend on each other during the training phase. MapReduce overcomes this by preparing the vectors from sequential input files during the pre-processing stage, and each cluster exploits these vectors during the training phase. Accuracy scores doesn't follow a consistent comparison pattern across different datasets. Experiments show that Mahout's Naïve-Bayes Classifier model having better accuracy scores than MLlib's classifier. Increasing the number of nodes is expected to reduce the amount of work on individual computing units. Experiments show that adding more clusters to the system significantly boosts Spark's performance. However, MapReduce doesn't achieve that much improvement in performance as we add new clusters to the environment. The reason is that Hadoop's operations are input-output bound because of its disk dependency. Adding more clusters to the system means more input-output operations made by extra nodes on the shared disk. As a conclusion, experiments demonstrate that Spark is about 5 times faster than Hadoop in terms of the execution time of the training phase. This rate is proportional to the number of clusters in the system, since Spark scales better with the increasing number of the nodes in the cluster. However, the performance of Spark degrades as the input workload gets larger. So we can say that Hadoop is better when we have restricted amount of clusters. Our results show that Hadoop provides consistently better classification accuracy figures than Spark. As part of our future work, experiments could be repeated with different classification algorithms or with any other data mining tasks to observe the impact of different machine learning techniques on performance. Furthermore, we would like to investigate the behavior of the employed systems with larger datasets. I would like to express my special thanks to Mr. Ali Çakmak for his guidance and support through my research. And I am also grateful that Aselsan compensated the registration fee and supported me for this study. Thank you for listening.